Hello, good afternoon. Sorry for the delay. I just got delayed a little bit. Oh, only you are here. I think Rebecca, she left the meeting. Am I audible? Yeah, sorry for the delay. Hi Camilo, hi Yvonne. I think someone's mic is making noise. Is it?
I think it's mine.
Yvonne, yeah. Okay. So yesterday we were talking about the weak solution. Now, I think at this stage, we are clear with the two kind of solution, and let me start, and then we can talk about that. Just let me share my screen. It's visible. Okay. Yeah. So now we know that a number of physical phenomena can be formed by the hyperbolic conservation law. Can be formed by the conservation law. Now, the conservation law has a flux function and also has a density function. So, mu t plus fu of x equals to 0. When there is no source term, so this f is known as the flux function and this u is known as the density function. Density function means the variable which is changing with time, and the flux function, the volume of that density function will change across the boundary of the domain. On the basis of the nature of f, we can determine what will be the kind of the solution if we are provided with an initial condition. So, is there something wrong, Yvonne? So, a flux function.
No, everything's
There is
alright.
hiding, so I thought I said something wrong. Okay, so if this flux, the double derivative of this flux function is greater than 0, it means it is convex. I'm just reminding the previous thing, and if you get stuck anywhere, then please ask me. Convex function, then to solve this scalar conservation law, when I am talking about the scalar conservation law, it means u is function of x comma t, and that is belongs to a omega, that is contained in r cross r plus, that is one dimension. U is a single vector. So scalar conservation law, if u is belonging to the omega that is contained in Rn cross r plus, in that case we call it system of conservation law. So if this is a scalar conservation law and the flux function is a convex flux function, then for monotonically increasing initial data, we are going to get a continuous solution. It means there is no concept of weak solution. We are getting a continuous solution because the solution is defined in the whole domain. So there are two concepts. The solution is defined in the whole domain and the solution is defined in the piecewise domain. When the solution is defined in the piecewise domain, then it is called a weak solution. And when the solution is defined in the whole domain, then we say that it is a smooth solution and the solution exists for all the time t. So when f is a convex flux function and the initial data is monotonically increasing, in that case we are calling the solution exists for all time t. So basically we have a continuous solution, no concept of weak solution. Like we don't need to discuss anything further. We have our unique solution here. However, when this flux function is convex, but the initial data is monotonically decreasing, in that case the characteristic may coincide. In that case, the characteristic emanating from the x-axis may coincide, and we will encounter the multi-valued solution. It means the solution may break down after a finite length of time. So we need to define the solution in the piecewise domain. We need to define the solution in the piecewise domain. So that's bring the concept of weak solution. That brings the concept of weak solution. So when f is convex flux function and initial data is monotonically decreasing, we are not going here. No, we are stopped here. We have gotten the unique continuous solution. But when f is convex flux function and the initial data is monotonically decreasing, in that case the solution may break down, that the characteristic may coincide. So we are interested in the solution that is defined in a piecewise domain. That is defined in a piecewise domain. So we come across the topic of weak solution. Now yesterday we saw that there was a problem and we write two solutions. The solution was not continuous. It was a weak solution. It was a weak solution to the given partial differential equation. Now we could see that we have two weak solutions for the given partial differential equation. Do you remember that? We have two weak solution of the given partial differential. So when we come across the point of weak solution, then we may have more than one weak solution. Then what will be the criteria to distinguish unique weak solution? What will be the criteria to distinguish the unique weak solution? Then it comes the concept of the entropy condition that single out the unique weak solution, among the given weak solution. So I am going to discuss this entropy condition, and again I will remind the same thing. So if you have doubts, so in what case we are going to visit the entropy condition? When the solution is defined in the piecewise domain, is not it? When the solution is defined in the piecewise domain, then we are going to discuss this entropy condition. If the solution is continuous and there is no breakage, then we are not going to use the entropy condition, because we are getting a solution that is defined in the whole domain, and that is a unique continuous solution. Consider the equation ut plus u square over 2x equals to 0. X belongs to the real number, t is greater than 0, and u belongs to the domain omega that is contained in R cross R. So this is a scalar conservation law, and we know that this scalar conservation law is named as the Burger equation. This equation is named as the Burger equation, and the initial data is so if we focus on the initial data and on the form of the flux function, then we can see that our flux function is convex flux function and initial data is monotonically increasing. So we are going to get a continuous solution. There is no concept of weak solution, but still there might be solution can be formed, and we can check they can be weak solution. So I am forming the solution, and then I am going to discard that cannot be the solution of this given differential equation, and that will be discarded using the entropy condition. So suppose you don't know the concept of the monotonically increasing and the convex flux function. You don't know anything. I am saying that this is the hyperbolic PDE and this is the initial data, and suppose the solution breaks down after a finite length of time. Just suppose, you don't know anything. So if it has a jump discontinuity, then what will be the velocity of that discontinuity? Jump in the flux function over jump in the u. If there is a discontinuity propagating, so what will be the jump? So jump in fu over jump in u. That is u square over 2 over jump in u. Suppose there is a left state and right state. So ur square over 2 minus ul square over 2 and ur minus u. We already have solved this equation. Do you remember for both the equation? So s equals to ul plus ur by 2. And what is ul? 0. What is ur? 1 by 2. So this is the velocity of, if we assume that there is a discontinuity propagating in the solution of this differential equation, so the velocity of that discontinuity will be 1 over 2. That is dx over dt is, this is a curve x equals to capital XT. That is the curve of a discontinuity, and this curve is propagating with the velocity 1 over 2. So this suggests that we might have, and when you will be taking the integration, so xt will be, the curve will be coming t over 2 plus constant. So this constant is 0, so the curve will be coming t over 2. So x equals to t over 2. So this is the curve that is the curve of discontinuity, and xt. Before this, the solution is 0. So the solution is going to be like this, and after this, the solution is going to be like this. Is not it? Is it clear? Dx over dt is equals to 0. So dt over dx is equals to infinite. So this will be straight line, and that will be 45 degree. And this is the curve of discontinuity. Although here we can see that no curve is intersecting, that's why this kind of discontinuity is not going to propagate, but we have to discard them using a given physical condition. So in that case, the solution will be 0, 1, x is less than t by 2 or greater than, and x is greater than t by 2. Is this solution is continuous? No, because the left hand limit and right hand limit are going to be different at t by 2. So this solution is not continuous. So this is a weak solution. This is a weak solution. We know that this have a continuous solution, but just forget for a while, just forget that you know anything. So this is a weak solution. Now I am saying that a solution given by this form 0, beta 1, x is less than or equals to beta t over 2, beta t over 2 is less than x is less than or equals to beta 1 t over 2. If beta is a positive quantity, if beta is a positive number lying between 1 to 0 but not 0, so is this solution is continuous? Beta is any number between 0 and 1, but it is neither 0 and nor 1. So whether this solution is continuous or not? Is it continuous? No. It is not continuous, because when you will check the left and right limit at beta t over 2, then the left limit is going to be 0 and the right limit is going to be beta, that is lying between 0 and 1, and that cannot be 0, and for the same for this one end. So this solution is not continuous. So this is a weak solution of the given PDE, because if you will notice, if you keep t equals to 0, then it becomes 0, 1 and x is less than or equals to 0. It means it gives initial condition. It also satisfies the given differential equation. So this is a weak solution, but this solution is not continuous, but it is satisfying the given differential equation, and it is also satisfying the initial data. So this is a weak solution. Now we are very interested. We have two weak solutions of this given PDE. which one is physically relevant? Which one is physically relevant? So the Lex came and he said that if you are talking about the weak solution of the given PDE, then it should satisfy a given condition that is named as ULT is greater than S is greater than URT for convex flux. Now what is ULT? If this is the solution, ULT is 0. What is S? That is 1 by 2. And what is URT? That is 1. For the same, is it true? Can 1 be less than 0? So there is a contradiction. It means this is not satisfying the Lex entropy condition. This is not satisfying the Lex entropy condition. It means this is not possible. So this problem has only one solution, that is a continuous solution. It does not have a weak solution. However, if you see the problem, same problem, but just reverse the initial condition. Then in that case, this was going to be a solution. This will be a solution, like just keep it 1 and 0 here, and then ULT will be greater than S, will be greater than URT, and in that case, no, 0, 1. So this is going to be solution. This again not going to be solution. Yeah. In that case, we can check the solution. That was a weak solution. Do you remember about the weak solution of this differential equation? It was 1, 0 when x is less than or equals to t and by 2, and when x is greater than t by 2. This is again not continuous at t by 2. But it is a weak solution and it is also satisfying this criteria. Is not it? ULT is 1, S was 1 by 2. This was the required weak solution. Now I am writing a criteria. So this criteria is for convex flux function. What we will write for the general conservation law? For the general conservation law, with convex or concave F, a generalized or weak solution is called admissible or physically acceptable if for each discontinuity propagating with speed S. What is S? Jumping flux function over jumping U. This is also called our Rankine-Hubiniot condition. This is also called
the FU jumping condition was in integral form.
Yeah. So this is also called the Rankine-Hubiniot condition. If there is a discontinuity that is propagating with speed S in the given solution, then a weak solution will be called a physically acceptable solution only when the inequality f dash ul is greater than s is greater than f dash ur is satisfied. So would you please open your assignment? Assignment 3. PD assignment. Assignment 3. So you can see that I have given you. Is this definition clear? I have given you ut plus u 1 minus u x equals to 0. So this is f double dash is u square. So f double dash is minus 2. That is a concave flux function. Is not it? And f dash u is 1 minus 2 of u. 1 minus 2 of u. Now we know that for the concave flux function, if the initial data is monotonically increasing, then the solution will be smooth or not. This is the concave flux function and the initial data is this. So whether the solution will be smooth or not? No. So there will be a discontinuity that will propagate. And what will be that discontinuity? Speed of that discontinuity. Dxt over dt is equals to s is equals to, sorry. Jump in f of u, jump in u. So what is jump in f of u? U r 1 minus ur minus ul 1 minus ul over ur minus ul. Please cross verify my calculation every time because I am very bad at calculation. Is it right, Camilo? Please. Yeah. So what is the value of ur? Ur is 1 and ul is 0. Okay.
UR was an integral.
Sorry?
UR was the value. I don't remember UR what value it takes. It's just like the limit from the right of the function.
What you want to ask?
I want to know like the value of UR and UL.
Yeah.
That's the limit from the right and the limit from the left.
This is the UR and this is UL. So when I am taking UR and UL 0 and 1, then I am getting 0. It's not it. So that's why I just keep it 1 by 2 and 1. In that case, we won't be able to determine the speed of this cone. That's why do you remember I told you take 1 by 2 and 1 and then interchange for this problem. So this is 1 by 2. Now, if we compute f dash ul, then 1 minus 2 ul. So 1 minus 2 into ul is 1 over 2. So 0 f dash ur is 1 minus 2, that is minus 1. So 0 . 1 by 2 plus 1 minus 1 by 2. So f dash ul is 0, f dash ur is minus 1. So here we can see that f dash ul is greater than s is greater than f dash ur. So what we are getting, 0 is greater than minus 1 by 2 is greater than minus 1. That is satisfying. So when you will be writing a solution in this form, then it is going to satisfy. It has a discontinuity. However, if you were getting 1 and 1 by 2 here, then you are not going to get any kind of condition which is going to satisfy this, because in that case you are going to get a solution which will be continuous. So you will not have a weak solution. I am telling you this thing because from here you can verify whether you have a weak solution or not. Whether you have a weak solution or not. So using the initial condition and using the flux function, at least you can check whether you have a discontinuous solution or not, if you forget the concept of monotonically increasing or decreasing, just with the help of the Lex condition. Is it clear?
For a solution to be weak, you have to make you have to check that it's piecewise continuous. And there's another condition, or there was like an equivalent condition.
Equivalent condition?
Yeah, not condition, equivalent like definition for a weak solution. You gave us two.
Yeah, so what I am saying that we are not talking about the solution, whether when we are able to derive the solution, then we can analyze whether it is a weak solution or it exists for all the time. That is not the reason. If you are not deriving the solution, but you just want to check what kind of the solution will be, so you can check from here. If this condition is satisfying, it means the solution will have a discontinuity. If this condition is not satisfied, it means there will not be a solution which has a discontinuity. This is an assumption. I assume that it has a discontinuity propagating with the speed s. And then we can see that it is satisfying for this initial data. It means it will have a discontinuity. It will have a discontinuity. However, because here I am not deriving the solution, because sometimes your flux function might be very difficult and you are unable to derive the solution. It is not that much easy to always, here it is easy to get the solution. When it was like this, then it was easy to get the solution. But suppose I am giving you a flux function of the form the sine of u square by 2 and then x, then it will be difficult to derive a solution, but at least you can check whether it will have a continuous solution or weak solution. Because in one of your assignment, I have asked about check no, I have given that write the entropy condition. So for the write the entropy solution. So for the entropy solution, you have to check whether that solution is satisfying this condition or not. F dash ul is greater than s.
When you say this condition, you mean the jumping condition?
Lex entropy condition, yeah.
Yeah. So okay.
So in the question number 3rd, calculate the unique entropy solution. So every time when the weak solution satisfies this entropy condition, we call it the unique entropy solution, and that is physically acceptable. Okay.
Okay, so we have to check that inequality for the entropy condition to hold, right?
Yeah.
Okay.
If you have any doubt, then you can ask. So you can see that when the Lex entropy condition, when the flux function is convex, it will reduce to ul is greater than s is greater than ur. However, when the flux function will be concave, it will reduce to ul is less than s is less than ur. So that's why we always stuck to the one condition, convex flux function, because it will be easier for us to remind those things. Is not it? Now comes the definition of shock wave. We already know the rarefaction wave. We already know the expansion wave. We already know the discontinuous wave. Now we are coming to the definition of shock wave. That is a very important definition. So a discontinuity satisfying the Rankine-Huguenot jump condition, the Rankine-Huguenot jump condition, and the Lax entropy condition is called a shock wave. So if in the solution of a given partial differential equation there is a discontinuity which is propagating with this speed, then if that solution is also satisfies this Lax entropy condition, if just focus on the statement, if you have a given partial differential equation with an initial datum, you compute the solution and you find out that the solution of the given partial differential equation has a discontinuity that is propagating with this speed. So whether the solution which you have derived is a weak solution, which is a unique weak solution or not. So to check the uniqueness, we apply this Lax entropy condition, and if that weak solution also satisfies this Lax entropy condition, in that case the obtained discontinuous solution will be known as shock wave. Okay, so first comes the definition of the discontinuous solution. If the solution is continuous, then we are done. That is a unique and we are not going to do anything. If the solution is continuous, so we are done. We have gotten the solution for all the time. But if the solution is not continuous, that has a discontinuity propagating with this speed, so there may be more than one weak solution. The solution is weak solution and there may be more than one weak solution. Now, to single out the unique weak solution, we need to check the Lax entropy condition. If that weak solution also satisfies the Lax entropy condition, in that case we call it a shock wave. Is it clear, everyone? So I would prefer to go to the lecture number 12. And this was the solution. Do you remember? And since here we could see that for the given differential equation, and the initial data was u of x comma, the initial data is monotonically decreasing. The solution is going to be discontinuous according to our theory. Now the solution which we computed was this. Can you check that this week's, and you can check that this solution, although this solution is continuous, but it has a jump at t equals to alpha. So we cannot say that it is continuous in the whole domain. It has a jump at t equals to alpha. Do you remember when x tends to alpha and t tends to alpha, this becomes unbounded. So we cannot say that it is continuous. Now can you check that this is a unique weak solution or not? Can you please check this condition? Sorry. Okay, so what is the speed of discontinuity here? F u over jump in u, and When we calculated it for this problem, it came 1/2. Now we need to check that whether this is a weak solution, because we can see that when x tends to alpha and t tends to alpha, this becomes unbounded. So it has a discontinuity at alpha. It has a discontinuity at alpha. Now it means it is a weak solution because it is not continuous in the whole domain. So if this is a weak solution, so whether this is a unique weak solution or not. So to check that it is a unique weak solution or not, we need to check this lax entropy condition. So this lax entropy condition, F dash UL is U L, F dash UR is UR. So whether this satisfies this or not. So you can see that 1 is greater than 1/2 is greater than 0. It means this solution is also satisfying the lax entropy condition. It means this is the unique weak solution of the given partial differential equation. Is it clear? I am telling you this because I have given you 2 to 3 consecutive problem in your assignment 3 and assignment 4, and that is using the same criteria, entropy condition. And today we are going to talk about the Olenek entropy condition. That will be the end of our topic, and that is very important in all over the theory. Do you want me to, do you want to note it down? Although it is not necessary. So now we know the weak solution. Now we know the Rankine-Hugoniot jump condition that is derived with the help of the weak solution. Now we know the lax entropy condition. Now we know the shock wave solution. Is not it? So how many definitions you know? Weak solution. Firstly, the hyperbolic partial differential equation, then the conservation law, then the weak solution, then the Rankine-Hugoniot jump condition, then the lax entropy condition, and then the shock wave. Next, we are coming to the elementary waves. Now, I have written the definition of the Riemann problem here, if you will see. But you already know the Riemann problem. I already have defined that if the initial data has a discontinuity at a single point, then we call the Cauchy linear partial differential equation with that initial data is Riemann problem. Is it clear? So there are 2 kinds of problem: Cauchy problem and then Riemann problem. Can you open the assignment number 4?
For the Riemann problem, we have just one discontinuity.
It may have more than one discontinuity. If it has more than one, then we call it generalized Riemann problem. But I am giving you only one discontinuity. Yeah.
Okay.
Yeah, you don't need to go on that. Just focus on the Riemann problem. So can you open the assignment? So just have a look at the first question. I am giving you the Burger equation. So the flux function is convex flux function. Now, using the method of characteristic, you have to solve, and I am giving the initial data. That is not a constant. That is not a constant. So that is a generalized Riemann problem. If the initial data is not a constant, then in that case, the problem with that initial data is called the generalized Riemann problem. And since it has a jump at x equals to 0, is it continuous or not? Would you please check? I don't think it is continuous. It is continuous? Okay, then there is no topic of the Riemann problem. Okay. However, that is a generalized initial data. The second condition, I am giving you a smooth initial data. It is a smooth initial data, not only continuous, it is smooth. The second one. Then just come to the problem number 3. It has 4 pieces of initial data. 1, 2, 3, 4. X is less than -1, then 1, -1. So it has a discontinuity at -1, at 0, at 1. It has 3 pieces of discontinuity. So that also comes in the category of the Riemann problem. It was just to show you so that you will not be confused, and now you can proceed. So that's why in the third problem I am talking about the entropy solution. When you will be deriving the solution, you have to check whether this condition is satisfied or not. The solution which you are deriving is satisfying or not. So basically, since the convex first function is convex, so you need to check this condition for the derived solution. Firstly, you will use the method of characteristic to derive the solution. It's fine. And since it is a constant, so then the solution is also going to be constant in every interval. Now you have to check, and I can see that monotonically decreasing, so it will have a discontinuity. It will have a discontinuity. So there will be S1, one discontinuity, and there will be S2, the second discontinuity. There will be two discontinuity propagating, S1 and S2. Because
I have a question about like all of this. But, well, not with respect to the jumping condition and the entropy condition, but I have a question about the assignment 3, where you have to build build the solution. But when you build the solution, it's easy to see that the right hand side of the UR and the UL are the same. Like, you can see the solutions will be the same as the initial conditions.
Yeah, you're right. That is the problem you need to encounter, to solve.
But I have a question about like when you get the function, you know what's the function, like the C2, you know like what the explicitly the function in between the intervals, like from, I don't know, 0 to alpha, like just some interval.
I am not giving you alpha, so you have to find out what will be the solution. You will use.
Yeah. The question I have is like, I was discussing it with Camilo, and I have like problems putting like finding the intervals of x and t of the 3 solutions, and that reduces to like analyze the plane and finding conditions, like more than finding, like impose conditions on t and on x, so that the solution will be continuous.
Okay.
So
I'm just giving you a hint. I'm not telling you everything. I'm just giving you a hint. What will be the characteristic? The characteristic will be this. Now, just focus on the UL. At x is less than or equals to 0, this becomes UL. Is not it? So x will be UL plus some constant xi. So the line will be this line, like x will be less than or equals to t plus xi. Because x is less than or equals to 0, the initial data is UL. So just keep it here. So when x is less than or equals to this, the solution is going to be the left, and when x is greater than
ULT plus,
that solution is going to be 1. So that is the hint. You need to you need to go through, you need to solve these things, and you need to understand. If you will not be able to crack this thing, then again we can discuss. But that is the hint. That's what we do in the software. How I write the
yeah, that's like the main problem.
ds over dt, and from here I got that character. I got the line. Before that the solution will be this, and after that the solution will be this. Is not it? Okay. So when the solution is discontinuous, this is the way which will divide the solution in 2 parts, and when the solution is continuous, the characteristic will divide it in two parts. I already have discussed in the very first example of the rarefaction wave.
Yeah, yesterday, right?
So
yesterday you solved like the rarefaction wave, and I was thinking, and Camila also was thinking about the
it
like
might be problem.
like
It might be the case that you will be getting like x is less than or equals to 0 greater than t. So in that case, because t is always positive, at t equals to 0, the solution is given. So for t is always positive. X is less than or equals to 0 and x is greater than 0. So I think you will be getting like this or something like that. You have to find it out.
Okay.
Actually, I checks everyone assignment, and if there is something wrong, I used to discuss in the class. If you are doing something wrong in your assignment, then I used to discuss with you. So in assignment, I would ask you, if you are able to solve only one question, still do submit your assignment on the time. Still, you do submit your assignment on the time, because I check the assignment and I check the time when you have submitted. According to that, I am giving the marks. This time I am stick with that. So if you solve only one question, still do submit. If there will be something wrong, I will tell you your mistake, where you have made in that mistake.
Okay.
Now, there is a stretching transformation, and we are going to see how does it affects the given partial differential equation. I don't think I will be able to finish the whole syllabus today, but let's see. Most of the time, when we talk about the solution of a hyperbolic partial differential equation, in most of the paper, you will go through the point of the self-similar solution. So what is the meaning of the self-similar solution? That is very important thing to understand here. So let's have a look at the self-similar solution. The differential equation is the same. So it may be noticed that the stretching transformation, x to a of x and t to a of t, where a, small a, is any positive numbers. What is this? We don't know. We are just transforming our coordinate x comma t to ax comma at. So we are taking the stretching of that coordinate. Then if we use this transformation, then this partial differential equation is unchanged. Do I need to show it to you, or it is clear? Do I need to show it to you? Anyone? So,
I didn't get the question.
I am saying that if we change our coordinates x to ax and t to at, basically we are stretching the coordinates. Then this partial differential equation will be unchanged. So do I need to show it?
No.
Okay.
It's translation. It's translation invariant.
T will be replaced with a del over del s, and x will be replaced with a, and a will go to the right hand side. So it is unchanged. So this transformation x to ax and t to at leaves both the equation This is the conservation law, equation number first, and this is the initial data, and 2 invariant. Thus, if u x comma t is an I forgot to tell you the most important thing, not most important, but just keep in mind. When I was talking about the weak solution, then I said that this weak solution will be the unique weak solution if it satisfies the entropy condition f of f dash ul is greater than s is greater than f dash ur. And if a solution is not a weak solution, like if the solution is not a discontinuous solution exists for all the time and it is continuous for all the time, then the condition will be reversed. Then it will satisfy this condition. Like in the research problem, we used to check both. For the smooth solution, we follow this condition, and for the non-smooth solution, we follow this condition. So this is just to keep in your mind. It is not written in book, but it is a way. If the solution is continuous, it exists for all the time, then for sure that is unique, so it will not satisfy. However, its reverse will satisfy. So this is just to keep it in your mind, because when we have a system of equations, if some of you are interested to see these things in any kind of research paper, then just write me an email and I will share you a very basic paper, and then you can see all these things in the research paper. And at some point, if you are not understanding, then I can tell you. So it is up to you. So I can send you a very basic research paper. Then if we have a system of equation and we derive the solution using the condition dx over dt equals to lambda I. Lambda I is I told you how it is lambda I, if you remember. Do you guys remember? Like we have a system of equation, and if Li is left eigenvector and Ri is right eigenvector, so just multiply Li from the left. So Li ut plus Lia ux equals to 0. Now what is the value of this Lia? Li lambda, can we write this? Because Li is the left eigenvector of the matrix A, so it will satisfy the matrix. And now this is scalar. This lambda is a scalar. In fact, I will write it lambda I because it is the eigenvector corresponding to the ith eigenvalue. Now take this Li outside. So ut plus lambda I ux equals to 0. Since Li cannot be 0, so ut plus lambda I ux equals to 0. If we use the method of characteristics, so as soon as this dx over dt is equals to lambda I, u becomes constant, because this is du over dt, del u over del t, dt over dt plus dx over dt, that is lambda I del u over del x. It means along this characteristic, that is dx over dt equals to lambda I, this solution u is constant. In that case, the characteristic is measured with the help of lambda I. That's why we talk about the real eigenvalue, because if the eigenvalues are not real, in that case we cannot talk about the real characteristic. We cannot talk about the solution in the real space. So that comes in the hyperbolicity. If we have the complete set of real eigenvalue, then we call, depending on the eigenvector, strictly hyperbolic, weakly hyperbolic, or hyperbolic. So this thing is very important. No one is going to tell you in the research paper. I will always ask you, make some sticky notes, and there are some important points which I used to tell you on the corner. Try to write it. It is useful for your further research. So this is a very important thing. No one is going to tell you. So why we calculate the eigenvalue and check the hyperbolicity, and then we talk about the characteristic solution in this. So this is the very important thing. Shall I erase it?
Yes.
So, sorry. Okay. So that was the point. When we discussed the characteristic solution, we discussed the reverse condition if it has a smooth solution, and we discussed this condition if it has discontinuous solution, and that gives us the condition on the variable, so that we are able to write the complete solution, complete set of solution. Because when we have a system of partial differential equation, we know that this will be the characteristic, but we also need some extra condition to single out the continuous solution and to single out the discontinuous solution. So this is the extra condition which we use in our research paper. Okay. So this is stretching transformation leaves both the equation number first and the equation number second invariant. Thus, if uxt is an entropy solution of, actually I went to this point. So when the solution is smooth, entropy.
I have a little question about like the when you have like the entropy condition, how that leads you to single out the discontinuous solution.
So we have seen that for the given problem, we do you remember? And
yes.
We have two given solution, that was weak solution, and when we use this entropy condition and we single out that it does not have a weak solution. No, none of them were the weak solution because it was not satisfying this initial condition. It has a discontinuity, but it is not satisfying this Lax entropy condition. So both the solution were not a discontinuous or weak solution of the given PDE. However, if suppose that might be possible. I am giving you the problem, I am giving you the solution. I am just saying that, okay, check that this is your solution or not. You will say that, oh, we can see that this is a solution of the given PDE, and since it is a piecewise continuous solution, so it is a weak solution. But I will say, no, this is not the physically relevant solution. You need to verify that it is physically relevant. Then you will come to the entropy condition, and then you will say that, oh,
so like one thing is like the acceptable mathematical solution, and the other is the entropy solution that makes you think it's a physical acceptable solution.
Exactly. Because there might be more than one solution, but what is of our interest? We are interested in.
Yeah, there's like a partial differential equations where you have like negative time that's in the domain of the function, but you cannot take negative times.
Yeah. So you need to be careful when you like this thing. This thing is very easy because we are following it for scalar conservation. Now that's why if you will ask me in the email, then I will send you a paper that will have 2x2 system of partial differential equation, and then you can see these beautiful things in your paper, and they are writing the research paper to publish in a good journal. So that is the research problem people are working. Like for small system, they have worked in the previous literature, but still for the complicated system, like still I am working on this kind of thing, but for more complicated system, it is not that much easier as it looks. So UXT is an entropy solution of first and two. So the meaning of entropy solution, I mentioned here entropy solution. So when it will be smooth, then we will verify the reverse condition, whether it is an entropy. We also call it entropy solution because it will be satisfying the reverse of the Lax entropy condition. So is an entropy solution of first and two, then for every constant a greater than 0, the solution u8 x comma t u of ax comma at is also a solution, since the entropy solution for a given initial condition is unique, since the entropy solution for a given initial condition is unique. We choose, it is up to you. You can choose a equals to 1 over t, 2 over 2 t, or 3 over 2 and obtain u of x comma t equals to u of x comma t comma 1. So as soon as you will be writing a to 1 over t, the solution can be written in the form of x over t, and we therefore look for the self-similar solution of the form. We therefore look for the self-similar solution of the form u x comma t is equals to phi of x over t, and consider the riemann problem 1 comma 2 with the uniformly convex flux function, and consider the riemann problem 1 and 2 with uniformly convex flux function, and ul is less than ul, then the convexity implies since this is a convex flux function, the solution is a unique entropy solution, and since it is a monotonically increasing, so the convexity implies f of ul is less than f of ul. This is just opposite to the Lax entropy condition. Is not like, no, it is not f, and the rare fraction wave is given by, and this is the case when the flux function is convex and the initial data is monotonically increasing, then we will be getting a continuous solution, that is an expansion wave or rare fraction wave, and the rare fraction wave is given by u of x comma t ul Now I am giving you a reason how to write this x is less than or equals to t f dash ul. Now I am giving you the range. Now you don't need to ask me how you will define the range in the given traffic flow problem. Can you see that? So if f is a convex flux function and the initial data is monotonically increasing, in that case you will be getting a rare fraction wave solution and the domain will be this. Is fine. Where phi x t solves f says, however, if ul is greater than ur, if ul is greater than ur, it means you have a convex flux function and the initial data is monotonically decreasing because ul is greater than ur. Then you will be getting the weak solution satisfying the entropy condition, is a shock wave and is given by, then the weak solution satisfying the entropy condition. What was our entropy condition? F dash ul is greater than s is greater than f dash ur. Satisfying the entropy condition is a shock wave. And the solution is given by where s is f of ur minus f of ul over ur minus ul. That is the RH condition. So if you have a convex flux function, then if you don't want to go to the method of characteristic, still you can write the solution in this form. You can write the solution in this form using this theorem, or you can say lemma. Okay, now the solutions of the Riemann problem for a scalar equation, namely shocks and rarefaction waves, are called elementary waves. So if I am giving you a Riemann problem, then either you will be getting a rarefaction wave or you will be getting a shock wave. Shock wave can be rarefaction. Shock wave can be determined using the Rankine union jump condition and Lax entropy condition. We need two conditions to determine the shock wave, and we only need one condition, that is the stretching transformation, to determine the rarefaction wave. So you can see that using this stretching transformation, we write the rarefaction wave solution, and in the further movement we use the RH condition and the Lax entropy condition to write this shock wave solution. So if you are given a single partial differential equation, a single conservation law, and general UR, UL and UR, and you don't know whether UR is greater than UR and UR is greater than, you don't know anything, still you can write both the solution, and according to the initial data one can pick up the one solution. So you can write the general solution in this form, and here everything domain is defined. Now you have two problems, like you have two problems for the vulgarization, and you don't need to follow the method of characteristic, you just can write the solution by using this lemma. Is not it? So this is the lemma, and the rarefaction and the shock wave, these are called the elementary waves. So the evolution, the study of the elementary waves is very important and very emerging topic in the area of the hyperbolic conservation law. Next, we come to the Lax Orlenic entropy condition. Do you guys have any doubt here? So there are different kind of admissibility criteria in which the author, the mathematician Orlenic, she was the first to give this admissibility condition. So she was the first to give this entropy condition, and she talked about a general flux function, whether it is convex or whether it is concave. So firstly, Orlenic formulated the generalized entropy condition. Generalized entropy condition means you don't put any kind of restriction on your flux function. We don't put any kind of restriction on our flux function. So Orlenic gave the generalized entropy condition, which applies to non-convex. I am writing just for the general, because when you have concave flux function, then still you need some kind of admissibility criteria to single out. So we can see that this Lax condition, it was much satisfied for the convex flux function. So Orlenic came and she said that, okay, when you have a non-convex flux function, you don't know whether it is convex or concave. In that case, you just need to apply this entropy condition and you are done. If this entropy condition is satisfying, then you are getting a unique weak solution. Just keep in your mind the continuous solution and the discontinuous solution. When the solution is continuous, we are done. We don't need to check anything. But when the solution is discontinuous, we need to use the Rankine-Hugoniot jump condition. And then using that jump condition, we need to find out the unique weak solution, and that will be find out using the lax entropy condition or the Olenek admissibility condition.
So if I'm getting everything right, all of this is going towards the uniqueness of a weak solution. We want to know like a method to obtain a weak solution that's unique.
Yeah.
That's the aim.
Yeah, that is your syllabus now, existence and uniqueness of the solution of conservation law of first order PD. So existence was the weak solution. Existence that comes in the category of the weak solution and Rankine units. So we are going to the uniqueness.
But there's not a weak solution, like a solution in a conservation law. Or there's always a weak solution, or you can have like a, I don't know how to say that, like a normal solution.
I'm not getting what you want to ask. Would you please repeat?
I want to ask if in the like realm of conservation law or the area of conservation law, we always talk about weak solutions, strictly weak solutions. That's the only kind of solution we are going to get.
Yeah, why we do so? Because we don't know. We have a general initial condition, so that's why we write the general solution. We also write the rarefaction solution, and we write the discontinuous solution, and we call it weak solution. So if the initial data will be monotonically increasing or decreasing according to the flux function, we will choose one of them. So every time when you are going to see a paper, in each of the paper, you will see that they talk about two kinds of solution. I am going to show you a paper just after this topic, and then I can show you. And then they use the lax entropy condition, and then they say that okay, this lax entropy condition, if the solution is weak solution, so we use Rankine-Hugoniot condition, and then we use the lax entropy condition to single out the weak solution. And if we have a smooth solution, then we need the reverse of the lax entropy condition to get some condition on the variable, but we don't need RH condition there.
Okay.
Yeah, I will show you a paper, but just let me finish this Olenek condition, and then I can.
Yeah.
I still have two topics like to trying to tell that Hamilton-Jacobi equation and Eikonal equation. So I have uploaded the note that is talking about the Hamilton-Jacobi equation. Yeah, I will finish soon. I think this section was really, this unit was really long. So according to this, the function uxt is an entropy solution of first. Solution of first if a discontinuity propagating with speed defined by f is equal to jump in f and jump in u satisfies the condition. Satisfies the condition. Can you see that in the lax entropy condition, we were not, what is the difference? Can you see that in the lax entropy condition, we were not talking about the equality, we were taking the strict inequality, greater than, but here we are normalizing, we are just relaxing something, like we are taking the equality, not a strict inequality. It's not it. So this is the admissibility condition. That's why it holds for the non-convex flux, non-convex scalar flux function. When the flux function will be strictly convex, this will reduce to f dash ul when the flux function will be strictly convex. So if you take and u is something between ul and ur. U is a point between ul and ur. So when your flux function will be convex, then you will get the condition f dash ul is going to be less than f dash ur. In the case when u is lying between ul and ur, and using this condition, this inequality will reduce to a strict inequality. However, for the concave, you cannot say that this inequality will be strict or not, because here you will lose that condition. So this is the Orlenic entropy condition, and I am not going to explain this thing which I am telling, because I have written each and every line in your notes very clearly. So you can see that for all u between ul and ur, this condition reduced to the compressibility condition, that is the lax entropy condition, and I am writing strict inequality here, when the flux function is strictly convex. However, for a general flux function, you will take the limit and it will not be a strict inequality. However, it will be a equality. It may be an inequality as well. So you will read this thing, and if you are not getting any point, then please do ask. Each and every line I have written here. Since it is including the non-convex flux function as well, so I am not going to explain it in a very broad way, and this thing is to you. Only the second entropy condition, you can also read this. So this was the entropy condition. The most important was the lax entropy condition. We already know that. So this is in the next class, we are going to talk about the Hamilton-Jacobi equation and the diagonal equation, and that will be the end of this unit 1 and 2, and then I will start the unit 3. But on the second hand, I would like to show you a paper in which they are computing a solution, and then you can take a look if you want some time. Okay. So can you see my screen?
I cannot see.
Sorry.
You're trying to show us like a paper, or?
Yeah, paper. I was just showing you a paper.
I can see. I just see like black background.
Right. So I was like, I told you that there are two kind of traffic flow problem in which they talk about the only velocity density of the cars, but this is a different kind of traffic flow problem. So this is the system in which they are writing the density of the cars and the velocity of the cars, and there are two equations. So what they are doing, firstly, they are deriving the eigenvalue of the system, and here u is the velocity, so the eigenvalue are going to be real for all the time. So either the eigenvalue is real, so it is a strictly hyperbolic, because they are distinct as well, so it is a strictly hyperbolic conservation law. And then they are talking about two kind of solution. They are taking this stretching alpha x and alpha t, and the solution is going to be the Riemann real fraction wave. So real fraction wave, can you see that? And then in the second half, because they don't know, here they are defining the initial data, rho plus minus and u plus minus, when x is greater than 0 and when x is less than 0. So we don't know whether rho will be less than rho plus will be less than rho minus or not. So we don't know that. So that's why they are defining both kind of solution. One, by taking this stretching transformation, then the solution will be of the form x over t, and then they are deriving this solution. Now you can see that the solution is derived, but there is some condition on u. So this condition is derived using the lax entropy condition. U is greater than U minus, rho is less than rho minus. So this is derived using the lax entropy condition. Next, there might be possibility that the solution is containing a discontinuity, so shock wave will arrive. So to discuss the shock wave, they are writing this sigma is S. So yes, jump in S equals to jump in the flux function upon jump in the density function. Can you see that? Is it clear? So S, that is the velocity of the discontinuity. Xi equals to sigma is a bounded discontinuous solution, and sigma is the velocity of the discontinuity propagating. So they are writing the Rankine-Hugoniot jump condition. Now after writing the Rankine-Hugoniot jump condition, they are deriving this shock wave solution, and here they are again putting this lax entropy condition to single out the unique shock wave solution. Unique shock wave solution. So this is the thing, like I just wanted to, and this paper you can see that this is published in 2023. So can you see that this thing which you are discussing here? Someone is saying something. Okay.
I just wanted to say, like, the all of this methods. I don't know why in physics they don't like teach us how to approach this, because like it has like a lot of applications, and it's basic. Well, it's not basic PDE theory, but I think that if, like myself, like a physicist, I had like this knowledge of PDE, maybe it wouldn't like have like the title of I don't remember the title of it was Forum of Physics, the journal of the paper you showed us.
The paper which I show you.
Yeah.
This is a very good
physics of fluids.
Yeah, this is a very good journal.
Yeah, but actually, I was thinking like most of the physics that is done like in the graduate area, they have like a lot of pure mathematical treatment. But as a physicist, I've never like realized how important was like the pure mathematical like treatment of a PDE. So like it's pretty interesting.
Yeah, this is very interesting. That the physics is that when you are writing a system, so in the writing the system, you need a lot of physical assumption. Like if you are writing a traffic flow problem that I was showing you, so you need
an intuition, like experimental
assumption. Yeah. So, but to solve those things, to show the solution, we need these mathematical things like what we have done in the previous classes. So this unit was not a very like this. I can say that this was the very basic, but in the same way it was advanced basic, not the basic. It was the advance of the basic PDE. So you just revise all those things. You have Thursday, Friday, Saturday, Sunday. You have 4 days to solve the assignment 3 and to revise those things. And like in the next half of the Monday, we will approach to the Laplace solution. That is a wave equation. Laplace is a wave equation. Okay. So we will go through the. I will give the classification of the second order PDE, because there is also the classification of the second order PDE, hyperbolic, parabolic, and elliptic. So this Laplacian equation is, I think, elliptic. Isn't it? So we are going to discuss those things, like the very basic of those things, and then we will proceed, and then we will again go to the higher topic. Yeah, but meanwhile, I would like to ask, just revise these things, and if someone asks something, someone will be asking me for some paper, then I can give you the old paper in which they are discussing everything very basic way. So yeah, just go through this, and it is a very interesting topic, I would say. So okay,
Thanks.
nice meeting you.
If you saw me like talking, I was talking with Rebecca because Rebecca and I were like discussing some concepts like during the class. I'm like at the side of
Sorry.
I was like talking with my muted microphone,
Ah, okay.
and I was talking with Rebecca.
Ah, okay.
Yeah, we are taking the class, so we were like discussing at some point some things we thought about, like,
Ah,
oh, this condition, oh, this.
that's great.
So,
Actually, I was going to discuss with Rebecca because I don't know whether she is getting the things because I don't have a good interaction with her. Actually I wanted to do, but I think she don't talk too much, so I could not talk. But in the exams, even I haven't seen her house. Does she looks like? I haven't
yeah.
seen her face. So if you may say hi here, can you ask?
Yeah. O sea, dice que sí puedes, no sé cómo decir. No sé, hola. O prender tu cámara.
Oh, see. So I haven't. Hi,
Hola.
Yeah, so I haven't seen your face. So I could not communicate with her. So it would be great that you are discussing these things in all of you, like Roberto is here, Ricardo is here. So you can make a group and you can discuss the things. And at some point, I know that you guys might be facing the difficulties because of English. But again, I said it, just be consistent in the class, and by the time you are going to understand everything. Like I remember the Camino, when he came to my first ODE class, I think it was difficult for him to understand me. It was very difficult for him, but he was so consistent that he understand everything now, and he respond very well now. I'm really impressed. Like you already know, you speak very good English, but it was difficult for him.
Camilo, it's an expert.
Yeah. So now I can feel that he is understanding everything, and I really feel great. Like, don't you feel, Camilo, that your English has been improved with time? So I would just ask you, just be consistent in the class, and if you will pay enough attention to the class, then everything is going to be very easy. And you can ask me a lot of questions. I am here to give the answer. I am here to explain the things. If I want to be able to explain in another this way, then I will try another approach. So just be consistent. The thing is going to be easier with time. Yeah, the PDs. This PD is not a basic partial differential equation, rather than it is a advanced course. And most of this is the master and PhD course, if you remember. This is a master and PhD course. So I won't say that it is very easy, but at the same time, I won't say that it is very difficult. You just need to pay attention, and it is the thing. I am also learning with all of you because I am not an expert. I am just explaining the things, and sometimes I find something and I also note down in my notes that, oh, I got this thing new. So this is the thing. I would just ask you to be consistent, and everything is going to be fine. And please do discuss in between all of you. You might discuss some papers, like if someone will write me an email, and then you might discuss some paper. That would be great. You are deriving the rare section. Like at this stage, I still remember some of my colleagues, like some of my juniors. They are working on the Riemann problem, but they are unable to derive this rare fraction wave solution for a Riemann problem for a 2x2 system of PDE. So it would be great that if you can solve it. Yeah, that is because you are going to be a PhD student. So this is the way you can.
I hope.
I believe.
I believe in all of this structure.
I'm saying that you guys hope, but I believe on you that you guys are going to get a PhD position and a good PhD position. You just need to
go through these things and just solve that stuff. No one is brilliant on this earth. Everyone do a lot of hard work. No one is going to tell you, oh, you are working this much. No one is going to tell you. So you just need to solve these things. Be consistent and everything is going to be fine. Yeah. So in your exam, the exam will be on the next to next Monday. Yeah, I haven't announced it. The class today I will announce it. The next to next Monday, and I am going to ask the question that will not be outside of the course, like the entropic rare fraction shock wave, and I will give you a problem that has a convex flux function. Still, I haven't made the paper, so I will prepare the paper, and that will not be outside of the course. It is going to be formation of the PDE, classification of the PDE, because it is the combination of unit first and two. So just go through your assignment, solve all the questions, go through your notes, read all the topics, and yeah. And I would like to ask you. You may also discuss to the Roberto. For him, it is a little bit difficult to communicate with me, but with you guys, it will be very easier, and he is doing great. So you may discuss in your group, and you can solve the problem in a group. Yeah. So this will also increase your knowledge.